Good day, everyone. We want to have another section of physics class, and the topic at hand is machine. So we'll continue from where we actually stopped, but we are going to introduce it from the beginning, at least to have everyone carried along. So thank you. So this a kind of better definition for machine. What's the meaning of a machine? A machine simply means any device which makes work easier, faster, and generally reduces or removes drudgery through the application of little effort to overcome a large resistive or resistance force. Um, that is how simple a machine is. But to quickly illustrate what a machine is, for instance, now, if we have to cut or to dice or to chop our okra, we have options. We may choose to use our fingers, we may choose to use knife, we may also use a grater. Which one do you think we may be engaging doing that and still be at least not putting up any form of complete concentration? I want to believe everybody will subscribe to greater. So that is just simply that we are making a machine to perform our task for us. If also we need to wipe this board, if I should use hand, it may appear rough, but if I should use a wiper, you see it will be so neat and completely wiped out. So that is how simple a machine is. Then I must still remind us that we have different categories of machines. Essentially, we have two classes of machines. The first one is simple machines, and the other one is complex machines. When we are talking of simple machines, we are talking of devices like cutlasses, knives, tin cutters. For us to cut a tin, especially this milk tin, we can rub it against the floor. We may also use knife to cut it. We may also use a tin cutter. Which one is most suitable for the operation? That is tin cutter. So meaning that it will make it easier. It will make that thing we've done to appear neater as well, and it will remove unnecessary effort. So that is how a machine works. Now, uh, types of complex machines include washing machines at home. Imagine it has various components. Then we also have a blender. So it also has lots of components as well. So we are not looking into the aspect of complex machines, but today we are looking through the aspect of simple machines. And for you to have a better understanding of what simple machines are as well, let's take for instance now, if you are driving or you are you are embarking on a journey, suddenly you have a punctured tire. How do you think we can replace the punctured tire with our extra tire? Oh, the best thing I know, it will be to call about 20 able guys to lift the car for us and to remove the screws. You can see this one would appear so difficult, but we should just bring out our wheel spanner with our jack. What 20 able men may not be able to do, our jack, which can even be operated by someone who is not even muscular, who is not so strong. So that's how a machine works. So that is what we are trying to introduce to us tonight, and we are going to look through the calculation aspects of it as well. So to cut the story short, we have it clearly stated here that we have two categories of machines: simple machines, and we also have complex machines with their examples well stated. Then we have terms associated with machines. What are these basic terms which are associated with machines? We have mechanical advantage. This is also known as force ratio. We also have velocity ratio. We have efficiency. Then we have ideal machine, or which can as well be called perfect machine. So Within a few minutes, we take down the meanings of these terms. So we'll have to start with mechanical advantage, which I will have to represent as MA. So mechanical advantage of a machine is defined as this is defined as the ratio of load to that of effort. All this mathematically is given as mechanical advantage equal load over effort. So which can be stated as L over E. So this is the mathematical relation for mechanical advantage. And why is it being referred to as force ratio? It is being referred to as force ratio because load is measured in Newton. It's a kind of force. What type of force? Resistive force or resisting force, which is the one which we are trying to overpower, which we are trying to overcome. Then we have effort as well, which we are applying, as also being measured in Newton. So meaning that load is a force, effort is also a force. So that is why mechanical advantage is equally being referred to as force ratio. So this makes mechanical advantage to have no unit. So it has no unit. So 2, we have velocity ratio. What's the meaning of velocity ratio of a machine? Velocity ratio is defined as the ratio of the distance moved by effort to the distance moved by load. So this is known as the velocity ratio of a machine. What is this telling us mathematically is that velocity ratio is given mathematically as effort distance over load distance. So we have this, which can as well be put as E distance over load distance. So I would like to use a diagram to illustrate this two perfectly. So let me use a lever to illustrate how we easily memorize what mechanical advantage and what velocity ratio are. So going by this, we have this, using a lever to represent this. If this is represented as load, and the effort which we are trying to apply, is this effort, and this is load. This is effort. From this fulcrum or pivot, from the pivot, what is the distance? How far is the effort from the pivot? We call that distance of the effort. While the load, how far the load is from the pivot or from the fulcrum, we call it load distance. So we have the load distance, we have the effort distance, we have the load, we have the force, which are the 4 parameters which come together to form the constraint components of both mechanical advantage and the velocity ratio. So from here, we are focusing on an ideal situation. What's the meaning of an ideal situation? This may make me to just briefly tell us or introduce us to ideal machine or concept of ideal machine or a perfect machine. Let's see this. From the concept of conservation of linear momentum, we have this as clockwise moment is equal to sum of clockwise moment is equal to sum of anti-clockwise moments. So we are just applying this, which will give us what? Load multiplied by load distance is equal to effort multiplied by effort distance. We can see this too. So now going by this, let us write the relation for mechanical advantage, which is load over effort. Now equal. Now just draw this line. Which one forms a partner with the effort? The one which forms partner with the effort is what? Effort distance. Meaning that if we should carry out cross multiplication, we are going to get E multiplied by ED. Then which one forms partner with load? That is load distance. So truly, we can deduce from here that this one gives the relation for mechanical advantage, which equates to velocity ratio. And when we have these two being equal, we'll be talking of an ideal situation, which takes us to the concept of ideal machine. What is now the meaning of ideal machine? Let's check this one critically well. What's the formula for mechanical advantage? Is what? Load divided by what? Effort, which is what we have here. What is the velocity ratio? Effort distance over load distance. Meaning that for any ideal machine, mechanical advantage will always be equal to the velocity ratio. And now, what is now the meaning of ideal machine? So just hold on. In a short while, we will understand this one quite well. But I want you to get how mechanical advantage relation is obtained, so as well as the velocity ratio. Now, let's pick from where we stopped. That's an ideal machine. What's the meaning of an ideal machine? An ideal machine is any machine with 100% efficiency. It's any machine whose efficiency is 100%. So, efficiency, ideal machine is any machine which is 100% efficient. That is the meaning of ideal machine. This is also known as a perfect machine. It is also known as a perfect machine. Now, let me say this. How do you really determine that a machine is perfect, or for you to have a better understanding of this? We all know here, whenever we put on a generator, the generator is meant to supply electricity. Let me now ask this question. Is it only electricity it always supplies? No. It will come, there are a lot of things which will come with it. It will equally supply unwanted noise. It will equally generate unwanted heat. So, meaning that the generation or production of sound in a generator or Production of heat in a generation will definitely reduce the efficiency of a machine. The power, the strength it is supposed to use in supplying electricity, it must have equally used it to supply heat, which is not useful, as well as sound, which is not wanted. So that is why it is very difficult to have a perfect or an ideal machine in a practical sense. Still, it is quite possible. In factories, when you go to factories to buy vehicles, to buy cars, there is a kind of test they always subject their products to, for you to know that the engine is in a very good condition. They may ask you to enter into your car, which you are trying to buy. Then they will place a coin on its bonnet. A coin will be made to stand this way. By the time you start the engine will not vibrate, engine will not make any sound. So, meaning that the engine is in a very good condition. So, such can be assumed to be very close to being 100% efficient. So, that's the concept of ideal machine. Then I will seize this opportunity to make you know that most of the calculations we go through in generating the what? The basis for velocity ratio. The assumption is that the machine is ideal. So that's why you see that mechanical advantage will always be equal to velocity ratio. Now, note this. Note, in an ideal machine, one, mechanical advantage is always equal to its velocity ratio. Two, work input is equal to work output. You have this. Then three, efficiency is equal to 100%. So with this, you just have to try to understand this, that in an ideal machine, mechanical advantage is always equal to the velocity ratio. So which is what I've just applied here, that mechanical advantage is equal to velocity ratio. And we went through the what concept of conservation of linear momentum. There are some of clockwise moments about a point is equal to some of anti-clockwise moments about the same point. Then we are taking this position of pivot as a reference point, and you can see how far the effort is from the pivot, so as well as how far the load is from the pivot, so which is known as load distance, and this one is known as effort distance. So you can see here that truly mechanical advantage is equal to velocity ratio. Work input will always be equal to work output. Then efficiency is equal to 100% for an ideal machine. Next will be, so let me make this the third one. Then the fourth one will be the efficiency. Efficiency is represented is this. What is the meaning of efficiency? Efficiency simply means now see, efficiency simply means, literally means how suitable a machine is for the purpose which it has been designed for. For instance, A knife is designed to fulfill the function of cutting. At a time when the knife is bought new, you can see it will cut things swiftly without wasting any time, without any stress. It keeps cutting, keeps cutting, keeps cutting. But over a period of time, you see it begins to do what? To go blunt. When a knife turns blunt, it means that the efficiency, the workability will be reduced, will be lower. So meaning that its efficiency becomes lower. So that's just the fundamental concept behind efficiency, and that is what efficiency simply means. How how perfect or how suitable a particular machine is for a purpose for which it has been designed. So, mathematically, I'll have to take us through the mathematical relation for efficiency. Efficiency is given as this: efficiency equal work output work output over work input multiplied by 100 over 1. You can see this. Work output ideally is expected to be lower than the work input, meaning that work output will be a fraction of the work input under normal circumstances, under normal situation. So from here, let's check this. Let's go. So let's go through this. What's the meaning of work output? Let me put this as this: efficiency equal work output over work input times 100 over 1. So now, for you to have a better understanding of what work output and work input, what they are, say this, let us assume that this is a grinding machine. So it has this where we collect whatever. This is our grinding machine. Now, let us assume you put your pepper in this. Then we are to collect our pepper here. We are to collect our pepper here. So, are we going to say that, let us assume that we have 100 grams of pepper here. Will all of 100 grams come out? No. This one, now please try to have a better understanding of this. Here, we are putting in pepper. We are exerting efforts. And whatever we are receiving through this place will be what we are going to take home for cooking, for whatever. Meaning that this one is our load. And you will believe with me that this one will never be up to 100 grams as the one which we are introducing. So this one load may be, let me say, 80 grams. So I will actually explain this one later. But I want you to have a better understanding of the concept of effort as related to machines and what? Load. Now, if we want to go through this, let's now compare to this. If this is our effort and this is our load, this is the what? Load distance. This is our effort distance. Now, don't forget that work is equal to force times distance. So now, let's now check the work input will be equal to a particular force times a particular distance. Which of these two sides will give us the input Is it side 2 or side 1? Is it the effort side will give us the work input, or the load side that will give us the work output? Now check to this. Load is the what? Output, meaning that this side it will give us the what? Work output, while this side will give us work input. So meaning that work input is a function of what? What type of effort, force? Because we are dealing with two forces. We are dealing with the effort force and we are dealing with the load force. So this input will now be effort multiplied by effort distance. Now, secondly, work output will be a function of which of the two forces? It will now be load multiplied by load distance. So these two will be what we are going to incorporate into this formula. So please and please have a kind of better understanding of this my diagram. We have this one as a kind of grinding machine. See, this is our grinding machine. We are introducing, through our efforts, we are introducing 100 grams of pepper, and we are to receive at the other end, which will be the load which we are going to collect from the grinding machine. This one, meaning that work output is a function of a particular force, which is load. Work input is a function of a particular force, which is effort. So, and now I'm using this lever to explain it. On this side, we have the load, and on this side, we have the effort. You can now see what is work input now. It's a function of effort and what? Effort distance. So, same thing is applicable to the work output. Work output is a function of what? Load and what? Load distance. So please try to understand this very well. So now efficiency is now given as work out over work in times 100 over 1. You know in to be input. Then work out now is equal to load times load distance. Then work in is equal to effort times effort distance. So now incorporate these two into the original relation. Efficiency equal work out over work in times 100 over 1 equal load times load distance over effort times effort distance times 100 over 1. So that is our efficiency. So from there, efficiency is now equal to, check this one, we can write this as load over effort multiplied by load distance over effort distance times 100 over 1. So efficiency, now recall that this load over effort we earlier came across this. Load over effort is given as what? Mechanical advantage. This one into brackets. This one is the what? Inverse of the velocity ratio. So for us to relate this one, to write this one in terms of velocity ratio, it becomes 1 over velocity ratio, which is the inverse of velocity ratio multiplied by 100 over 1. So efficiency is equal to mechanical advantage over velocity ratio times 100 over 1. So I want to believe that I've taken you through how to really understand the terms related to simple machines, which are mechanical advantage, velocity ratio, efficiency, and ideal machine. And for this aspect of efficiency, we have it as what? Work output over work input. It may as well be written as efficiency equal power output over power input times 100 over 1. How? See this. Power is equal to rate of doing work or rate of energy consumption. So if we should write this one as work done per unit time. So meaning that work is equal to product of power and time. So meaning that if we have work input is equal to power input over what? Power input times time taken. Then work output is equal to power output times time. So this now becomes efficiency is equal to work out over work input times 100 over 1, which is the same as what is work output? Power output times T over power input times T times 100 over 1. So efficiency is equal to T will cancel T. We have power output over power input times 100 over 1. So we have this mathematical relation for efficiency as well. But before we leave these aspects, I have to make you understand that if we are considering the work inputs, the work inputs may be taken as this as well. See this? Work inputs may be equal to useful work done times work done against friction. If I want to say this to a layman, for the person to just have a kind of complete understanding of this one without going through terms, when you call work inputs equal useful plus waste. No. So work input is equal to useful plus waste. Useful what? Useful work done plus that's useful work done by the machine plus what? Work done against friction. So we have this as well. So we will try to solve questions on what we've learned so far. So in case you have any questions to ask, you are very free to drop the question. I will, by God's grace, attend to the questions. So this is just the first part of the class. So we are going to answer questions on this, then we are going to switch into the next part, where we are going to discuss the various types of machine or various classes of machines. So thank you for watching through.